For this sequences and series section, not only do we need to balance calculation and manipulation with intuition and visuals, but we also need to balance what we're currently learning on each slide with what our overall goal is for this section. The goal of this whole section is to approximate values of functions by approximating those functions as polynomials. Since a polynomial is a sum of terms of x with non-negative integer exponents, we can think of a polynomial as a sum of powers. In this way, a polynomial of degree n is p of x, and in another way, this summation, also known as a series if it is infinite, is just a list of terms, also known as a sequence. This section therefore starts off with sequences, and then series, and then power series, but no matter how focused the slide is, the purpose of that slide is for us to ultimately approximate values and functions. A lot of ideas of limits for functions can be analogously applied to sequences, since sequences can be thought of as a function that only take positive integer values as arguments. A sequence is an ordered list of terms, and the entire sequence is denoted by this. While functions have limits, sequences have limits, with n being an element of positive integers. For most of this presentation, we will consider infinite sequences in series, which relate to an unending amount of terms. On the left, the sequence and the function have the same limit of 0 as they go off to infinity. But on the right, the sequence has this limit, but the function does not have a limit as x approaches infinity due to oscillations. Sequence. An infinite sequence is an ordered list of terms, and the entire sequence is denoted by this. Note that a set is a collection of objects where order is not important. A sequence has the limit, and we write this. If we can make the terms an as close to L as we like by taking n sufficiently large, that is, the values of an approach L as n approaches infinity. If the limit exists, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. Sequences can diverge by going off to positive or negative infinity or by oscillating. Series. An infinite series is the sum of terms of an infinite sequence. Let Sn denote its nth partial sum. If the sequence of partial sums, that is, sequence Sn, is convergent, and if the limit exists as a real number, then this series is called convergent. If sequence Sn is divergent, then the series is divergent. We write this where the number s is called the sum of the series. Supposing that these are convergent sequences and c is a constant, we get this and this. The squeeze theorem. In essence, when a sequence lies between two other converging sequences with the same limit, it also converges to this limit. If the limit of an equals L, and the function f is continuous at L, then the limit of f of an equals f of L. Regarding series, if these series are convergent, then constant multiple and addition-subtraction are convergent. If the series from n plus 1 to infinity converges, then the full series also converges, since a finite number of terms does not affect the convergence or divergence of an infinite series. The monotone convergence theorem. Every bounded monotonic sequence is convergent. A sequence is bounded if it is bounded above and bounded below for all n greater than or equal to 1. A sequence is monotonic if it is either increasing or decreasing for all n greater than or equal to 1. In particular, a sequence that is increasing and bounded above converges, and a sequence that is decreasing and bounded below converges, similar to an asymptote for a function. A telescoping series is a series whose partial sums eventually have a finite number of terms after cancellation. Thus, the telescoping series converges when the limit exists and diverges when it does not. For a convergent case of the telescoping series, consider a series where an equals 1 over n plus 1. Here is the limit an, and here is the sum in partial fractions. Note what happens to Sn, and note the limit of Sn as n approaches infinity. Proof for the convergence theorem of telescoping series. Here is a statement of the theorem. Proof. We'll consider the cases when limit Bn exists and when it does not. Limit Sn exists when limit Bn exists, and so the series is convergent. Limit Sn does not exist when limit Bn does not exist, and so series is divergent. Thus, the telescoping series converges when the limit Bn exists and diverges when it does not. The divergence test. If the limit an does not equal 0 or does not exist, then the series diverges. Equivalently, if the series is convergent, then the limit an equals 0. The divergence test is inconclusive if the limit an equals 0. That is, we cannot say anything about the convergence or divergence of the series. Here is the flowchart. Proof of the divergence test. Here is a statement of the test. This will be a proof by the contrapositive. If the series is convergent, then the limit an equals 0. Then we have the following. Since the series is convergent, the sequence Sn is convergent. Ultimately, we have limit an equaling 0. Note, this test is inconclusive if the limit equals 0. That is, we cannot say anything about the convergence or divergence of the series. For the sequences Rn, where R is a common ratio, we have the following. From our knowledge of exponentials and from what is seen on the graph, we can summarize our findings as the following. The geometric series test. For a geometric series, if the absolute value of the common ratio is less than 1, then it converges and its sum is this. If the absolute value of the ratio is greater than or equal to 1, then it diverges. For a divergent case for both the divergence test and the geometric series test, consider 2 to the power n, where we're always adding something positive and increasing. For a convergent case of the geometric series test, consider 1 over 2 to the power n and how it equals this. Although the series is convergent, this is an inconclusive case of the divergence test since we'll later see a series with limit an equaling 0 that diverges. Here is the flowchart. Proof of the geometric series test. Here is a statement of the test. For the geometric series, consider the cases regarding the common ratio r. If r equals 1, then we have the following. If r doesn't equal 1, then we have the following. For absolute value r less than 1, limit Sn equals a number, and so the geometric series converges. For r in these cases, limit Sn does not exist since the sequence Rn diverges, and so the geometric series diverges. The integral test. If the series has an analogous function that is continuous, positive, and decreasing, then the series converges if the improper integral converges, and the series diverges if the integral diverges. For an inconclusive case of the divergence test, consider the harmonic series 1 over n. Although the limit an equals 0, we can prove that it diverges based on the p-series test, which is based upon the integral test. Although this series is divergent, this is an inconclusive case of the divergence test, since we saw earlier a series with limit an equals 0 converge. For a divergent case of the integral test, consider the harmonic series 1 over n and its analogous function, that is continuous, positive, and decreasing. The improper integral becomes this, which diverges. Here is the flowchart. Proof of the integral test. Here is a statement of the test. The terms in the rectangles are the areas. We will prove that the convergence of the improper integral implies the convergence of the series. Let f be a CPD function and let f of n equal an. Consider the rectangles of height an and based on segments here. The sum of the areas of the rectangles is less than the integral of that CPD function. Then we have the following. Here, m is a finite number because the improper integral converges. The sequence of partial sums is increasing. The sequence of partial sums is increasing and bounded. By the monotonic sequence theorem, the sequence of partial sums is convergent. That is, the series an is convergent. We will now prove that the convergence of the series implies the convergence of the improper integral. Since the series is assumed convergent, its sequence of partial sums is convergent and therefore bounded from above. Then we have the following. Make a CPD function where f of n equals an with rectangles of height an and based on segments. The sum of the areas of the rectangles is greater than the integral of that CPD function. Then we have the following. Because m is a positive real number, the improper integral converges. Remainder estimate for the integral test. Suppose f of k equals ak, where f is a continuous positive decreasing function for x greater than or equal to n and series an is convergent. Then we have the following. The terms in the rectangles are the areas. If the series stops at n, it will be between the left and right improper integrals. And if Sn is added to each side of the inequality, considering that Sn plus Rn equals S, then we have the following. The p-series test. For a p-series, 1 over n to the power p, if p is greater than 1, the series converges. If p is less than or equal to 1, then the series diverges. Here is the flowchart. Proof of the p-series test. Here is a statement of the test. For the p-series 1 over n to the power p, we'll consider the cases when p is less than or equal to 0, p is equal to 1, and p is not equal to 1 greater than 0. Then we have the following. Therefore, in cases where p is less than or equal to 0, the series 1 over n to the power p is divergent due to the test for divergence. If p is greater than 0, then the function f of x equals 1 over x to the power p is continuous, positive, and decreasing on this interval. For p equals 1, we have the following, and so the integral diverges. For p not equal to 1, we have the following. If p is greater than 1, then we have the following, and so if p is greater than 1, the integral converges and equals this. If p is less than 1, then we have the following, and so the integral diverges. Altogether, since the integral converges if p is greater than 1 and diverges if p is less than or equal to 1, the integral test will show that the p-series converges if p is greater than 1 and diverges if p is less than or equal to 1. The following examples will be useful for the upcoming comparison tests. The direct comparison test for positive series an and bn. If an less than or equal to bn and series bn converges, then series an converges. And if bn is less than or equal to an and series bn diverges, then series an diverges. For a convergent case of the direct comparison test, consider a series that yields terms that are smaller than the terms of a convergent series. For a divergent case of the direct comparison test, consider a series that yields terms that are larger than the terms of a divergent series. Here is the flowchart. Proof of the direct comparison test. Here is a statement of the test. Denote the partial sums this way. Since both series have positive terms, the sequences of partial sums are increasing, and we have the following. By the monotonic sequence theorem, sequence Sn is convergent, and so series An is convergent. With Bn less than or equal to An, by part 1, if series An is convergent, then series Bn is convergent. By the contrapositive, if series Bn is not convergent, then series An is not convergent. In other words, if series Bn is divergent, then series An is divergent. The limit comparison test. For positive series An and Bn, if the limit An over Bn is a positive real number, then either both series converge or both series diverge. For a convergent case of the limit comparison test, consider a series that yields terms that eventually behave like constant multiples of the terms of a convergent series. For a divergent case of the limit comparison test, consider a series that yields terms that eventually behave like constant multiples of the terms of a divergent series. When the limit equals 0 or infinity, we cannot say anything about the convergence or divergence. A divergent-convergent pair of series could yield a limit that is 0 or infinity. Consider the divergent 1 over n and the convergent 1 over n squared. A divergent-divergent or convergent-convergent pair of series could yield limits that are 0 or infinity. First, observe that both series 1 over n squared and 1 over n cubed converge. Second, observe that both these series diverge. Here is the flowchart. Proof of the limit comparison test. Here is a statement of the test. Let small m and big M be two positive numbers such that small m is less than c is less than big M. Since the limit of the ratio is c, the ratio is close to c for all large enough n. Thus there is an integer big N such that we have the following. If series Bn converges, so does series big M Bn, and by part 1 of the direct comparison test, series An converges. If series Bn diverges, so does series little m Bn, and by part 2 of the direct comparison test, series An diverges. The alternating series test. For a series An that equals this, if we take the absolute value of the terms, if the terms get smaller and the limit of the terms equals 0, then the series will converge. For a convergent case of the alternating series test, consider the alternating harmonic series. The red squares are the An terms, and they oscillate positive and negative, and decrease in absolute value. The black squares are the partial sums, and although they oscillate, the oscillation gradually gets smaller. A series An is called absolutely convergent if the series of absolute values is convergent. Consider the alternating 1 over n squared. Here we have the following. So it converges by the alternating series test. Then the absolute value of this series equals 1 over n squared, and this converges by the p-series test. So the alternating 1 over n squared is absolutely convergent. A series An is called conditionally convergent if it is convergent but not absolutely convergent. That is, if series An converges but series absolute value An diverges. Consider alternating harmonic series. Here we have the following. So it converges by the alternating series test. Then, absolute value of the alternating harmonic series is the harmonic series, and this diverges by the p-series test. So the alternating harmonic series is conditionally convergent. If a series An is absolutely convergent, then it is also convergent. Thus, you can prove convergence by proving absolute convergence. But if series absolute value An diverges, then it is inconclusive concerning the convergence or divergence of series An. If series An is an absolutely convergent series with sum S, then any rearrangement of series An has the same sum S. But any conditionally convergent series can be rearranged to give a different sum. In fact, if series An is a conditionally convergent series and R is any real number, then there is a rearrangement of series An that has a sum of R. Recall that the alternating harmonic series is conditionally convergent. Then we have the following. Note that this last line is a rearrangement of the first line. Thus, we can rearrange terms and obtain different sums. Here is the flowchart. Absolutely convergent and conditionally convergent. Proof for the alternating series test. Here is a statement of the test. Consider the even and odd partial sums separately. Let's work with the even partial sums first. Due to I, sequence 2n is an increasing sequence. All bracketed terms in star and b2n are positive, so sequence 2n is bounded above. By the monotonic sequence theorem, sequence 2n is convergent, and let S equal limit S2n. Now, let's work with the odd partial sums. Since the even and odd partial sums converge to the same value of S, we have limit Sn equals S, so the sequence Sn is convergent, and thus the series is convergent. Proof for the absolute convergence test. Here is a statement of the test. A series AN is absolutely convergent if the series of the absolute values of its terms is convergent. Since we have this, we have the inequality. Since the series AN is absolutely convergent, series absolute value AN is convergent. So series 2 absolute value AN is convergent. Using the direct comparison test for series with positive terms, this is convergent. Then we have the following. Since series AN is the difference of two convergent series, it is also convergent. Alternating series estimation theorem is the following. In words, the size of the error is at most the absolute value of the first neglected term. This is because S lies between any two consecutive partial sums Sn and Sn plus 1. The ratio test. For a series AN, if the limit of the absolute value of the ratio is less than 1, then it is absolutely convergent. If the limit of the absolute value of the ratio is bigger than 1 or infinity, then it is divergent. When the limit of the absolute value of the ratio equals 1, then the ratio test is inconclusive. Consider the limit of the absolute value of the ratio of these geometric series. That is, consider the limits of the ratio of consecutive terms an plus 1 and an. With geometric series, the ratio test has ratios that are constant, and so the limits don't do anything. For other series, the ratios wouldn't be constant, and so the limits do something. For a convergent case of the ratio test, consider a series that yields terms that eventually behave like a convergent geometric series. For a divergent case of the ratio test, consider a series that yields terms that eventually behave like a divergent geometric series. For an inconclusive case of the ratio test, consider the divergent 1 over n and the convergent 1 over n squared. Both the divergent and convergent series have limit absolute value of the ratio equals 1, and so the ratio test is inconclusive in that case. Here is the flowchart. Proof for the ratio test. Here is a statement of the test. To prove part I, we'll make a direct comparison with a convergent geometric series. Since the limit L is less than 1, there exists a real number R such that we have the following. The left series converges by the direct comparison test because the right is a convergent geometric series since R is greater than 0 less than 1. Then we have the following. Since convergence is not affected by a finite number of terms, the series absolute value an is convergent, and so series an is absolutely convergent. To prove part II, we'll show that this would fail the test for divergence. Then we have the following. Thus, the series is divergent by the test for divergence. To prove part III, note how series where limit of the absolute value of ratio equals 1 could produce different results, like these series, which are absolutely convergent, conditionally convergent, and divergent, respectively. The ratio test is inconclusive. The root test. For a series an, if the limit of the nth root of the absolute value is less than 1, then it is absolutely convergent. If the limit of the nth root of the absolute value is greater than 1 or infinity, then it is divergent. When the limit of the nth root of the absolute value equals 1, the root test is inconclusive. Consider the limits of the nth root of the absolute value of these geometric series. That is, consider the limits of the nth root of the terms an. With geometric series, the root test has roots that are constant, and so the limits don't do anything. For other series, the roots wouldn't be constant, and so the limits do something. For a convergent case of the root test, consider a series that yields a rearranged version of a convergent geometric series. Then we have the following. For a divergent case of the root test, consider a series that yields terms that eventually behave like a divergent geometric series. For an inconclusive case of the root test, consider the divergent 1 over n and the convergent 1 over n squared. Both a divergent and convergent series have limit of the nth root of the absolute value of the terms equal 1, and so the root test is inconclusive in that case. Here we have the following. And here we have the following. Here is the flowchart. Proof of the root test. Here is a statement of the test. To prove part I, we'll make a direct comparison with the convergent geometric series. Since the limit L is less than 1, there exists a real number R such that L is less than R is less than 1. Then we have the following. By the direct comparison test, the left series converges because the right is a convergent geometric series since 0 is less than R is less than 1. Since convergence is not affected by a finite number of terms, the series absolute value an is convergent, and so series an is absolutely convergent. To prove part II, we'll show that this would fail the test for divergence. Here we have the following. Thus, the series an is divergent by the test for divergence. To prove part III, note how series where the limit of the nth root of the absolute value an equals 1 could produce different results, like these series, which are absolutely convergent, conditionally convergent, and divergent, respectively. The root test is inconclusive. Although a flowchart helps organize the tests, the form of a series is the deciding factor in picking which convergence-divergence test to use, and often you have to manipulate a series into an easier form or compare it to a series with an easier form. Thus, although the components of a series might hint at a particular test, you might actually pick a different test after you've done some work. Additionally, even if you found a test that works, there could be other tests that are just as valid. Here is the flowchart. A summary of divergence test, form tests, no negative term tests, and possibly negative term tests.